Welcome everyone to fall quarter and welcome to CS329A. I hope you made it to the right class. This class is on self-improving AI agents. Anyone made it to the right class here? Yes? Okay. How many of you are here and doing masters at Stanford? Okay. PhD? Okay. Few of you, and then undergrad? Okay. So masters is the big crowd here. Okay,
There's a good balance. Yeah.
It's a really good balance. So we'll introduce ourselves. So I'm Akansha. I have been working in large language models for a while, and I'm adjunct professor at Stanford, and I'm also in research at a startup called Reflection AI.
Hi, I'm Azalia Mir Hosseini. I'm an assistant professor in the CS department, and Akansha and I met each other when we were at Google Brain, yeah, back in the day, and then Google DeepMind. And I also worked on Claude at Anthropic and Gemini at Google DeepMind. And we are so excited to teach this course again. This is the second time we're teaching. Of course, we have made some updates both to the lectures and also the way we are kind of conducting everything during for the course, and we were just so amazed by the amount of interest for people to join this course. So we are excited to have you here.
The course website is at cs329a.stanford.edu. We have updated the website in terms of all the lecture materials and the papers that you'll be reading, as well as what's the homework schedule to expect, the project proposal and project structures as well. So in today's lecture, we'll start with an overview of large language models, just how the scaling trends have evolved over the last 5 years, and then we'll focus more on what we will cover in this class. And then from there, in the second half of this lecture, we'll cover the course logistics, and that part you should pay a lot of attention to because that influences your grades. So let's take a look at an overview of the trends for large language models. So one of the aspects that has been mind-blowing since GPT-3 came out is that that as you scale up the number of parameters in a model, they get better. And what this means is that language models like BERT and T5 were good, but as we increased the number of parameters, they got really better. They perform much better. And what this led to is something called a scaling loss for large language models, which are used in building the base model for the pre-trained base model. And as you increase the amount of compute, so there are 3 graphs here, as you increase the amount of compute on the x-axis, the loss function on the y-axis goes down, and the more compute you have put in, the more the test loss goes down, which leads to a better model. So that was one big aspect that led to GPT-3 and then all the subsequent ChatGPT, Palm, Gemini, and so on. And then similarly, as you increase the data set size on x-axis, the test loss goes down further on y-axis. So that's another aspect of another axis of scaling that leads to better language models. And the third one is of course parameter count. So if you increase the number of layers in a transformer or the amount of parameters that are there in the language model, that improves the loss value, and that leads to a better model. And this has been the foundation for a lot of this has been the foundation for a long time until last year, where this was starting to hit some kind of a saturation point. So from 2018 to almost 2024, this graph is a little bit outdated, but from 2018 to 2024, as the model size has gone up, almost consistently, we have been increasing the size of the model. So you started with something like BERT was 340 million parameters, GPT-2 was 1.5 billion parameters, and then GPT-3 was 175 billion parameters, and then say Palm was 540 billion, and then there was a bunch of subsequent models, and GPT-4 is estimated to be there, which is like trillions of parameters. So you can imagine that there has been an exponential growth in just the model size for large language models. The large stands for that they're growing in size, and that has been one of the key areas in which the models have been getting better. So why do we care about the models getting bigger? What does this lead to? So as I was explaining, that as the models get bigger, they continuously improve in performance on natural language benchmarks, on various other benchmarks, reasoning benchmarks, and so on. And then other interesting aspect that I will show you in a moment is that they learn how to do few-shot learning. So earlier you have to fine-tune the model for a specific domain, but just by giving a few examples, the model can follow that template and reason in that same vein, which makes it extremely easy to prototype things. And then the third aspect is that as the models become bigger, they have emergent behavior where the capabilities like reasoning only emerged in larger models. So just to understand few-shot learning or zero-shot learning here, so if the model is given a question like, or a task like translate English to French, it's able to give, so this is called a prompt, like it's given a task, translate English to French, and then it's asked to translate cheese to whatever is the French word. If the model can predict the answer without actually being trained on the specific task, then that would be called zero-shot learning. And then few-shot learning, in addition to giving the description of the task, you're also giving a few examples. So in this particular case, it's given translate English to French, and it's given a few examples of the translation from English to French, and then it's asked to translate cheese, and it's able to translate that. And you can see that this capability shows up in the large language models across a large number of tasks, and that has been one of the key areas that GPT-3 and PaLM and other models enabled, and then that subsequent innovations came from reasoning aspects of this. So on the reasoning side, as the models have become bigger, they have this emergent behavior of reasoning, which Azalia will tell us a little bit more about.
So as the models become bigger, not only we have this kind of a predictive scaling loss property that we kind of know how the loss function is going to go down as we throw in more compute data and parameters in the model, there are new kind of behaviors that appear in the model that they didn't have before, and we never could predict that until we had these bigger models and saw these kind of behavior in them. And one of the most important one of those behaviors is the chain of thought behavior. And for those of you who are not familiar with this, here is how it works. So in a usual prompting of a model, we can ask a model, in this case, a math problem, and then we can give it a one-shot example. Here is a math problem, here is the answer. Now I ask you a similar but not exactly the same math problem, and the model is expected to answer that. And the model might be able to use the one-shot example, or it might not be. But we can do better here by not only give an example, but also provide the reasoning or the chain of thought on how we got to that answer. So in this case, the question is a very simple question. Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many total tennis balls does he have now? And instead of just saying 11, like we're walking the model through how to get to this. Roger started with 5 balls, 2 cans of 3 tennis balls is 6, and 5 plus 6 is 11. And with this example, then the model has become familiar with the process to get to the answer, and it can leverage that to answer new problems. Well, obviously this is a very simple problem. Any like 1B parameter model nowadays can solve this. Doesn't need an example or a few shot or a chain of thought. But the chain of thought property itself is a property that is holding to this day, and it's a very, very important property for the reasoning models and all the thinking models and all the much of the progress that we have seen in the past year or so. Now, this property again appears as we have larger and larger models. Here are 3 models, Lambda, GPT, and PaLM. And as you can see, the chain of thought, and this is some results on some math data set. And these models, when they're smaller, like 8 billion parameter for Lambda or for GPT around 7 billion, they can't really benefit from chain of thought, like it doesn't do anything for them. But as they become larger, or for a PaLM model, again at 8 billion, it can leverage this chain of thought property and learn from the reasoning that is and the process that is provided in the context in order to solve problems better. And not only that, there are other kind of abilities to solve new tasks as we increase the size of the models. Like, for example, models can all of a sudden solve mod arithmetics better or solve a word unscramble problem just by having this larger size and this property. You see that all of a sudden it appears at a certain size. And because of all of this, we still, as in frontier companies and labs, are still interested in pushing the scaling laws and not only get the natural kind of progression, but also we will see more and more of these kind of emergent behavior that is going to be very important. Now, a little bit of history here. So ChatGPT was launched in November 2022. Obviously, it was one of the most successful kind of apps or software ever created. The time to reach 1 million users for it was 5 days, which is significantly faster than many of the other famous software that you can see there or services that you can see there. And there were pieces of kind of innovation on top of just scaling up the parameter size of the model that were very important to make ChatGPT what it was and to make that kind of leapfrog and over the previous models like GPT-3 and so on. And two important pieces here were the instruction tuning and the reinforcement learning from human feedback, which we are going to briefly mention in the next slides, but throughout this course, we are going to learn more and more about them. So let's first, and then we're going to learn about all of these in more details, but let's just take a step back and see how the process works. So the pre-training step is the step with the beginning of any language model training. That's the easiest step, and we just train the model to predict the next token out of all sort of text and data and so on. And then this is the fine-tuning step that was a key differentiating factor for a model like ChatGPT. And let's start with the first aspect of fine-tuning, which is kind of alignment with human preferences. So when a model is pre-trained, it has no sense. It has seen all data on the internet, in the books, everywhere, but it has no sense of like what is right and wrong and what is. It just statistically knows about the state of the world, but it doesn't exactly know things or know how to follow instructions. So the next step in training these models is the step where we try to steer the AI models to follow the goals and preferences and values of humans. And this is still a big problem. It's a big issue. We haven't like mastered it yet, but as the models become, as we progress, models are becoming better and much more kind of like powerful in the things that they can do. So it turns out that we can fine-tune the models to be aligned. For example, here are some graphs that show what if we take our base model that's just pre-trained and fine-tune it for things like sensibleness or safety. And these are data that we have collected. These are high-quality data for kind of showing the model what we mean by what's safe and what's unsafe, or what's sensible and what doesn't make sense. And these are like more highly curated data that we pass to the model for fine-tuning and to make the model more aligned with the values or the preferences of humans. So going back, let's just walk through this process again. So the first stop when we take a pre-trained language model is fine-tuning with next token prediction, which follows the same process as pre-training, but this time on data that is much more higher quality. For example, this could be data from books, creative essays, data that companies pay a whole lot, millions of dollars or hundreds of millions of dollars potentially to buy this data that's really high quality, and then we fine-tune the model on those, and the model becomes much better as a result of that. The next step is instruction tuning. And by instruction tuning, what we mean is that we show the model, again, traditionally in the past 2 years, this instruction tuning data is like a combination of human-generated data or templates and the synthetic data. But the way this instruction fine-tuning works is that we do have instruction and then question-answer pairs where the model learns how to follow the questions and answers them. For example, here, an instruction tuning dataset could be about the weather, like, please answer the following question: what is the boiling point of nitrogen? And then this is the answer. Or we can have chain of thought fine-tuning, where we show the model how it can walk through a process to get to the answer, and then we have the label, we have the result over here, and this is like these pairs of like questions and instructions and answers. And again, this data set is very there's a lot of effort that goes into this data set, and the quality of data set and the generality of it has a lot of impact on the quality of the model that we get at this stage. And after this point, then the model becomes more and more like the models we see today. Like, you can ask them questions, you can go back and forth with them. They have this sense of like how to perceive a question and how to walk through kind of some sort of like process to get to an answer. And the next step after instruction fine-tuning is this process of using human preferences and fine-tuning the model based on that. And this process is called RLHF, or reinforcement learning from human feedback. The way this is different from the previous step is the way we create the objective function and create the data. So in this case, instead of like just creating some supervised prompt and labels, we are basically creating a reward model out of human preferences. So companies spend a lot of money asking humans, sometimes experts, sometimes just humans, normal humans, about questions and the answers generated by the model. And we ask the humans to rate them to see which one is correct and which one is not correct. And that's how we can create some sort of a reward model here. And this reward model is instead of human, then we can use the reward model in order to kind of like guide the parameters of our LLM towards generating answers that are in line with this reward model. So basically, we want the generations by the model to be such that this reward model says, yes, these are good generations. We're going to learn more about this here, but we wanted you to have the high-level idea of what RLHF means, and we can have different types of reward. For example, we could ask the model to reward a pair of answers based on their correctness or helpfulness or specificity or harmlessness, all sort of reward functions that we can define. And depending on how we want the models to be and what we care most about, we can weight these different reward models and kind of use that in the RLHF process. So these steps at a high level, of course, there's a lot of effort goes into that, but like pre-training and then fine-tuning on higher quality data, instruction tuning, and RLHF were the core kind of components that made a model like ChatGPT over something that existed over all the large models like GPT-3 and prior models. So that made a huge difference in how good and capable the models were. So that was very cool up until last year or a year and a half ago. Pre-training and then fine-tuning were the big pieces. But since a year and a half ago, it turns out inference is also a frontier for making the models much more capable. And that opened like a whole lot of new research and directions and ways that we can make the model better. So let's talk about it a little bit. Like, this is the work we did in my lab last year. Last summer, it was called Large Language Monkeys. And it's kind of inspired by the infinite monkey theorem, and it's related to inference scaling. How many of you have heard of the infinite monkey theorem? Okay, that's a good amount. So the idea of the infinite monkey theorem, what it says is that it's not proven, but what it says is that if you have a monkey and a kind of a typing machine, and then we keep letting the monkey type all day, forever, after some time we will have the works of William Shakespeare in the things that the monkey types. So we were inspired by that to name our project, but the idea here was that let's have the LLM be the monkey, and let's ask the model over and over again to solve a given input problem. You can think of it as parallel sampling or parallel generation. So instead of asking the model once to solve the input problem, you can ask it many times. And also, let's assume you have some sort of a verifier or selection mechanism, so you can pick which one of these generated responses were correct. And then you output that in your system. That becomes the final output. So the model, instead of generating one answer, generates many, many answers. And then your verifier selects which one of them is correct and then outputs one of the correct ones. You can think of a verifier as, say, some unit test. If the problem is generating code, the verifier could be the unit test that we run against the code, and we see which one of the code generations passes all the unit tests and so on. The reason this can be a possibility here is that models there is some variance in the way the models generate responses. It's not deterministic. And you can even control the variation in the model responses with this thing called temperature. So you can force the model or encourage the model to generate more different responses as you ask a question. And here, now let's see some of the results of this repeated sampling. For a bunch of tasks like math and coding benchmarks, we increase the number of samples per problem from 1, which is the normal one, to 10,000. And here we are showing the coverage or the fraction of problems that are solved by at least one of these samples. And what we are seeing here is that, so the red line, the red dashed one, was the GPT-4o model. And while these blue and green lines, which were the Llama 8b, Llama 3 8b, and 7EB, were worse than GPT-4o model with one sample. But if we increase the number of samples from these models, in all of these cases, they do better than the GPT-4o model. And what it says is that it kind of seems like the models already know a whole lot more than what you get out of them when you just ask them once, right? So this is the kind of the underlying property of inference scaling, because it seems like we can get a whole lot more capability and problem solving kind of ability from these models if we just bring in this inference scaling. Here we are showing repeated sampling, but there are many other ways to do that. And so the reason it's called inference scaling is that we are not touching any of the parameters of the model. The model is fixed, and we are just like at inference time, we are creating different ways to kind of produce generations from the model and use them to generate higher quality answers or answers to harder problems for the model. The interesting part here is that for some of these problems, out of these 10,000 solutions, maybe like 3 or 4 of them were correct for a single problem. So it shows that how important it is to scale the inference to really get to the core capability of the models.
But what is the difference, whereas traversing all the possible answers and just teach out the correct like it's the number of samples that you have here. Like I saw, like you need like 10,000 times of samples.
Mm-hmm. So what's the question?
What is the difference of this with like traversing all the possible answers and just select one?
So the possible answers need to be generated somehow by the model, right? This is like the space of all possible answers to the model is way bigger, like right? We can like, if we do like a tree search or a random search, it's like way bigger, right? There's no way to like hit, even like, imagine like we are asking a human, like just sit down and solve this problem, right? There is a limit to, of course, there's no limit to humans' creativity, but there's a limit to how many generations we can have, right? Or if we randomize things, there's a whole set of answers that can be generated, and this is like highly sample efficient, right? 10,000 is not a whole lot, especially like, for example, for the math F to F, some of these problems are really hard, like IMO level problems. Like these are really hard problems that a tiny model like a 7 and a Llama 8B can solve.
I was wondering how does the latency compare? Like when you do actually generate all those samples, like compared to the GPT-4o, right? Like how does the latency compare?
Yeah, that's a great question.
Is there a trade-off there?
Yeah, of course there is a trade-off. And we touch on that in the lecture that I go more details towards this. The parallel samples, the good thing about them that they can be run in parallel. So from a latency perspective, that's less of an issue, but of course there is the frontier of cost trade-offs between how much compute you're spending, and we will look into that. And it varies depending on the type of and complexity of the problems. Yes?
Limited to when you have a verifiable domain like math and coding, and how do you handle it when you don't have?
Yes, great question again. It's a very hard, when you have verifiers, it's much easier. When you don't have verifiers, there's this whole set of research on how to train LLM as judge or LLM as reward functions or LLMs with tools becoming, and we're gonna learn about all of it. We have a lecture just dedicated to verifiers, so. Yeah.
Just a quick question, sorry. So, does this generalize to any positive temperature? So, like, as when the temperature goes to infinity, the kind of buff situation
yeah, we can't like have the temperature being too high because it's gonna be gibberish, like the model doesn't generate. So there's actually like a research project last year was like on tuning that or like figuring out what temperature. Usually if you go beyond like 1.2 or so, it's not great, yeah. Yeah. But there are other tricks that you can do to kind of make the model be more, like have more diversity in the type of answers, and that can be useful. All right. So let's look at this. So now, again, going back to the events of last year and a half, we had the DeepSeek model. I think it came out in December.
Christmas.
DeepSeek came out December 2024. Oh wow.
It's been a short time.
Short time or long time, I don't know, both. So when models like DeepSeek came last year, so basically a core kind of innovation in DeepSeek and then the O1 series, Gemini thinking and such were that now we are kind of bringing this fine-tuning and test time scaling together, because with this test time scaling and the models themselves, we have this new like kind of engine that we can generate a whole lot of synthetic data. For example, for problems like for math problems where we know the answer, we can have the model generate different like kind of answers that leads to that final kind of golden answer. Or for the coding problems, we can use the model to generate tons of data during test time scaling, tons of like quality data to solve coding problems, and that becomes part of our training set now. We can use that to fine tune the model to become better. So that kind of bringing these two together became a big piece in thinking models and reasoning models. And this is like an area that is like really, really important. There's just so much to be explored in this because again, it's kind of open-ended, right? There's no boundary in how good the models can become with test time scaling, and then bringing that back to the process of training the model or fine-tuning the model to become better is very exciting, and that's kind of the self-improving piece that we are very excited about. So a little bit about reasoning models. In the language monkeys, what we were showing was the coverage. Like if we had access to a verifiers, how we can see the kind of a log linear kind of scaling laws with the number of samples. And OpenAI, when they released O1 last September, they showed a log linear relationship this time with pass@1 for these like hard AMI benchmark, which is like a set of really difficult math questions. So as what they're showing here is that as they're increasing test time compute, and this is in log scale, the accuracy, the pass@1 accuracy of the model goes up, and this is for test time alone. Previously, this has been shown for training, but it's very interesting that this kind of scaling applies to test time as well, without changing the parameter count of the model. I'm going to walk you through like a few examples of how this kind of reasoning or test time scaling kind of works with models like O3 or Gemini. So one motivation here is that for difficult problems, just like humans think a lot more, spend a lot more time, or consider many different strategies, thinking models do the same. And they may use a chain of thought or other techniques to just go about like solving a problem. And there are different steps to that. For example, problem analysis is one step. Like the model first sees a problem and tries to analyze it. Then it can do the task decomposition, breaking a task into kind of simpler tasks that are more addressable. Then there is the self-evolution strategies where the model kind of tries something, sees the feedback, for example, runs some tests on the code, or uses a calculator, or just judges the answer, and it can use that feedback to optimize itself. There is self-correction, and there are alternative proposals. If something doesn't work, the model can backtrack and kind of try a different approach. These are some key principles that the model probably at some point pieces of it were trained as part of the training kind of data set, were curated by humans, but a big part of it is also the model kind of acquiring these skills during this fine-tuning process and RL from synthetic data process that the model does. Here is an example of like how O1 does analysis. The model is asked to write a bash script that takes a matrix and then outputs the transpose of that matrix. And the model starts with, just like humans, starts thinking, what are the important pieces here? So the user is requesting a bash script. Let's understand the input and output formats of this matrix, and so on. So the model just thinks itself. And amazingly, this kind of it's like a progression of chain of thought. This is like helping the model finding the answer. But the difference between chain of thought and this is that the model itself is producing this chain of thought. There's, of course, task decomposition. Like in this case, for the approach, the model thinks about parsing the input, building the matrix as an array of as an array of arrays, and so on. There's also self-correction, which is a big, important piece of, this is an important piece here. And I don't know how many of you have seen that when trying with the models, that you can see the thinking traces. And this is actually pretty common. Like the model starts something and then in the middle says, wait, there's something wrong maybe. Or and maybe I need to fix that. And it's very, very cool that the model can do that itself. So reasoning models, when they came out, like models like O1, compared to a model like GPT-4o, which wasn't a reasoning model, they tend to be better in, obviously, the reasoning task. For example, in math calculation, data analysis, programming and such, they all kind of outperform GPT-4o, but not necessarily in personal writing or editing text and so on. Yeah, question?
Do you think the gains due to this asking for a reasoning trace is due to actually the act of generating this reasoning trace, or just the act of asking the model to think or to use decomposition at all? Like, for example, if you said, like, think step by step, but don't generate out loud, like, don't actually generate through thought process, but just think about it without saying.
Yeah. I repeat the question, like, you're saying that do you think the reasoning models are becoming what they are is it based on the loud way of thinking?
I think the question is that, is it because of the reasoning traces, or is it because of things step by step, the chain of thought? Is it the data that's making a difference, or is it the instruction?
So the data basically has made the model kind of become a generalized thinker, right? Like the model can, and all of these steps, like breaking down a problem, being able to backtrack, being able to do analysis, all of these are these skills that the model has learned during this thinking optimization process that now generalize to other things, and they're helping the model right now.
So I think the other way to look at it is, as Alia presented, repeated sampling. So if you had just the base model right after pre-training, it would be able to do some reasonings, but at the same time, it will generate different kinds of reasoning chains, and it doesn't quite know which one is correct. So a lot of what we will cover in train time or test time scaling really comes down to it learns which is correct. So pass at 1 accuracy goes up, which is what you were seeing in the reasoning models, as opposed to like pass at K or coverage, which is what you were seeing in the repeated sampling results.
Yeah, and one other way to think around, like, yes, these kind of deep thinking and things that the model generates is actually helping the model every time to solve a new problem. And although it's like very expensive for the model to generate those things, still like we want them to generate those because it leads to better answers. Any other questions? Yes.
Do you use a different model for the reasoning step versus generating the final answer? Like maybe a smaller or like a purpose-built one just to the final answer use a large model?
So typically, the reasoning capabilities have gone up with the model size. So if anything, you would use the larger model for reasoning traces, and then maybe you collect a bunch of reasoning traces and then have a smaller model summarize the answer.
Yeah. So the models, like this is like, at least currently, things may change. They like their own traces more. Even if the traces are coming from a better model, they tend to like their traces, their own generated traces more. And we're going to talk about Swirl. This is one of the papers that
the multi-step reasoning.
The multi-step reasoning that we talk about. What if we bring a different model, not in the context of generating reasoning traces, but in the context of like evaluating and giving feedback. And we're going to see that as well. But models, surprisingly or not surprisingly, they like their own traces a lot more.
For reasoning models, how are they taught to reason? Is it a hard-coded set of sequences that are taught to do traces, or are they somehow fine-tuned to say, you need to do this much or this kind of thing, which will cause the traces to generate?
So I don't think there's a published piece of work that really covers this bit.
It's both, yeah.
But it's a bit of both, and at the same time, the base model did have the thinking capability to begin with, right? It would go do some amount of thinking. One thing that we will cover in the class is this notion of outcome rewards model and process reward model, and how you can use that feedback to get the model back.
Yeah, there's always some bootstrapping, like, okay, here are different ways, like chain of thought itself, which is heavily used in the instruction tuning of dataset, shows the model some ways of like how to think, and there could be like some templates showing for the model fine-tuning. But the things that the model, if you just ask it any question and it comes up with that, there's a whole lot of generalization in that. So models have gone way above like what the data or instructions that are used for training them. Yeah.
Yes.
Sample. Is there a way to make the number of samples dependent from people?
Please speak up.
The number of samples, can they be dependent on problem difficulty? I don't think there's a published piece of work that does that, but
yeah, we just so there is follow-up work to that where you use a reward model and then you can use that. So assuming the reward model has some notion of complexity, if you haven't solved it, it can guide like more sampling or whether it's repeated or parallel. But that's definitely an interesting direction to explore. Yeah. Okay, we need to get to the, we haven't, all right.
yeah, let me cover these. Okay, so you now know about large language models, and then you heard about how they learned how to think, and then they learned how to reason. So what's next, and why is this course relevant? So a lot of what this course is about is that large language models as chatbots or as reasoning models are basically still single turn, like or just like in the chat format. So they're not accomplishing a task for you. They're fun to interact with, but they're not necessarily accomplishing a task for you. What has happened this year, almost in the last few months, and it's been surprising, is that agents like Claude Code or Deep Research have really enabled people to do real-world workflows. So they're agentic workflows which can achieve tasks that you ask them to do end-to-end. So for example, if you want to go research and figure out where should I rent a home, perhaps for the entire year,